Welcome to the final bonus lecture of this APTS course on statistical computing. Now that the kind of formal, very serious part of the course is over and done with, it's a good opportunity to take a step back and think about statistical computing a little bit more broadly and the languages, programming languages we use to implement statistical computing in particular. So obviously, in the context of the course, I've used R throughout to implement all of the examples and illustrate all of the principles. There's a good reason for that. That's that R has become the standard language for doing academic statistical computing. But is that a good thing? Does R perfectly solve all of the problems that we have in statistical computing? Well, actually, I would argue not. And so this is maybe an interesting opportunity to have a little think about the programming languages we use, what's good about them maybe, what's bad about them, and whether there are languages that would do a better job, particularly in the context of the changing face of statistics. So I'm going to give a little bit of background. First of all, we're going to look back at how we've got where we are today. But then we're going to look forward, think about how we might do statistical computing better, what might make for better programming languages for statistical computing, and have a look at how that all works. So I'm going to argue that functional programming languages are better suited to statistical computing in kind of the modern age, and why that is, and what that has to do with compositionality and category theory, and scalability, right? So how that all links together. And then we can have a look at probabilistic models more generally. So in statistical computing, or in computational statistics in particular, we often work with probabilistic models. And so how does this sort of new, arguably improved way of thinking change how we think about probabilistic models and probabilistic programming languages and the way we approach probabilistic programming? And then I'll wrap up. So I think what's really important to understand is that statistics is really not the same as it was, say, 40 years ago. The field has completely changed. The technology that we use has completely changed. The algorithms have completely changed. Right? The whole subject is just very, very different to it was, say, 40 years ago. And looking ahead into the future, there's no real sign that the pace of change is slowing down. So probably it's going to change just as much, if not more, in the next 40 years. And this is very much the data age, right? We're just surrounded by data everywhere. Data science is becoming a very big thing throughout society, right? So it's not just about statistics being this very niche academic field. It butts up against lots of other disciplines like data science, machine learning, AI. These are very much in the public consciousness. Data is everywhere. And so it is a very different world, and it's changing all the time. So the context of that is actually changing technology. The way we do computing now, the way computers are just everywhere in even the tiniest devices that we carry with us all the time. Computers and computing are everywhere. Data can be gathered on all of those devices. High-speed internet can push data around. So the world is changing, and lots of people other than academic statisticians are working with data, doing data science, doing machine learning, doing AI. Most of the people doing machine learning and AI are not people who you would really think of as academic statisticians. So that's kind of interesting that most of the people working with data and doing interesting things with data are arguably not statisticians at all. And a very interesting thing to think about in that context is the fact that actually most of the people in those disciplines are not using R as their programming language of choice. So there are lots of people out there who are programming with data, doing data science, doing machine learning, doing AI, who are not using R. So that's kind of interesting. Does that impact on us? Are the languages that they're using better? Well, actually, in many cases, no. I would suggest not. They're just as bad, if not worse than R, in fact, in many cases. But it does bring up the whole question of what programming languages should be using. Why are different people using different programming languages? Will we still be using R in 20 years' time? Well, like it says there, I doubt it, and I really hope not. So what's wrong with statistical computing, and what's wrong with R? Well, R, as I mentioned, has become this de facto standard programming language for at least academic statistical computing. But R is really based on the S language, and the S language was a language designed by statisticians for statisticians in the mid-1970s, and that is at the root of all of the problems, right? So in the mid-1970s, computers were incredibly primitive. So the S language was designed for computers that are completely unlike any computer that exists today. And all of the algorithms that statisticians were using were very different to the algorithms they're using today. The kinds of problems they were thinking about, the size of data sets they were thinking about, the way you might scale your problems, all just completely different. And we just didn't know very much about how to design good programming languages back in the 1970s, okay? And so R, and the S language that it's based on, just has many very dubious design choices. So unfortunately, it's always going to be a bit of an ugly language. It's always going to be very slow and inefficient. And it's not really possible to change that without just completely breaking the language, in which case, it's no longer the same language anymore. And you could imagine doing some kind of incremental change over the next few decades, but I personally don't think that's a good place to start. In fact, in many ways, the tidyverse is an attempt to do this. So if you know about the R tidyverse set of packages, that's actually a way and a sort of a movement for bringing ideas from functional programming into R. And so, in lots of ways, I kind of admire and respect that. But fundamentally, it's still running on R. The R language is still fundamentally the R language, and so there's a very limited amount you can do to really change that base language and the fundamental flaws and problems that exist in that base language. So this problem of R being very slow and inefficient actually means that much of the R code base and much of the code in many R packages isn't written in R at all, because it's just so slow and inefficient that it's simply not suitable for many tasks in statistical computing, right? Which is a serious problem. And so what do people do? Well, they write code in other languages and then link it into R. And the languages they use tend to be languages like Fortran, C, or C++. They're all much faster than R, right? So that's why people use them. They're very fast and efficient in comparison to R. Well, that's great, except that they're actually all even worse languages for statistical computing than R. Yeah, they may be fast and efficient, but they're actually, also ancient languages that are very poorly suited to modern computing architectures and statistical computing generally. Okay, so it's a real mess, right? R is too slow and clunky and inefficient, so we write stuff in faster languages that are even worse than R for statistical computing, but they're just a bit faster, and then we end up with these different languages being glued together in a very unsatisfactory way, and the whole thing is really a bit of a mess. Okay, so how have we got into this state? Well, essentially, all of the programming languages that are commonly used for scientific and statistical computing were designed very much in the dawn of the computing age, right? Not only R. What else do people use? Well, MATLAB is probably even older than S. People use Python, so Python is probably the kind of one of the newer kids on the block, but that's still 30 years old. And again, 30 years ago, computers and computing were very, very different to how they are now. So if you think about how computing hardware has changed, think about how much we've learned about programming languages. So even if you're not a programming language theorist, right, you probably know how much statistical methodology has changed in the last 30, 40 years. You certainly know how much computers and computing has changed in the last 30 to 40 years. Of course, we know so much more about programming languages and what makes for a good programming language, and how to build programming languages that are better suited for modern hardware than we did 40 years ago. Of course we do. So it's kind of crazy that we're all stuck using these languages from the dawn of the computing age to solve modern tasks on modern hardware. It's just an unfortunate situation that we find ourselves in. Right, so let's just kind of start from a blank slate. How should we think about computing and computation? And obviously, we're thinking about statistical computing and data science in particular, but how do we solve problems generally? Well, the way we really tackle many big complicated problems is by breaking them up into little pieces that we can solve more easily. And we may do that recursively, break them into smaller pieces again, end up with problems that we can solve, and then glue those solutions back together again. So this process of sort of divide and conquer, it's sometimes known as, of breaking problems down, solving the problems, gluing the solutions back together, is really quite fundamental to how we think about computation, how we think about modeling, how we think about all kinds of things. So really, this notion of being able to compose solutions together and break things down into subproblems and glue the solutions of subproblems back together, this is kind of what I'm getting at by compositionality. That really should be fundamental to any programming language that we use, because that's just how we solve problems. But it turns out that actually the whole way we think about models in statistics and algorithms more generally really is not composable in this sense, right? It's not to say that there's no composition involved. Of course, many algorithms are recursive, of course, but the programming languages that we use don't really support naturally this compositional approach to problem solving and modeling more generally. So that's a problem. This mathematical theory of category theory is, if I had to kind of summarize category theory in a sentence, the mathematical study of composition, right? And so that's why category theory turns out to be relevant for us thinking about computation in a scalable compositional way. Okay, but we'll come back to that later. So what I'm going to argue is that functional programming languages, especially modern functional programming languages, which are strongly influenced by category theory, turn out to much more naturally support this compositional view of computation. Okay, and they lead much more naturally to scalable models and scalable algorithms, and also as a byproduct, they much more naturally take advantage of modern computing hardware, which also has the same compositional nature. If you think about it, we now have a computer. The computer has multiple processors in it. Maybe each processor has multiple cores. So that kind of breaking down computation and scaling it and gluing the results back together again is very much how computer hardware is developing as well. And so if we have a programming language that more naturally supports this compositional view of working, then actually that lends itself very nicely to this more compositional nature of modern computer hardware as well. Okay, and I'm also going to argue that actually expressing algorithms in this more functional categorical way, it's actually more elegant, it's more concise, it's less error prone, so it has lots of what you might call intangible benefits, aesthetic benefits, but actually it also has a lot of tangible benefits, and in particular the ability to automatically take advantage of modern hardware, automatic parallelization of algorithms to run on multiple cores, automatic distribution of algorithms to run across big computer clusters in the cloud, etc. All of this becomes much more simple and natural when you start working with these functional programming languages. So how is it that we're all using these so-called imperative programming languages if functional programming is such a great idea? Well, that is a very good question, but we are, and the roots of it are really much deeper than the superficial syntax of languages, right? So you see people fighting about the relative merits of R and Python, right? But R and Python are actually incredibly similar languages. They just have, some very superficial semantic differences, some very superficial syntactic differences, but fundamentally they're actually very similar languages. They're both actually very strongly based on Lisp. So how is it that we are all using these languages that are very imperative in nature? Well, I suspect that it's got a lot to do with the fact that we think about algorithms in a very imperative way. So, much deeper than any particular programming language, the whole way we think about algorithms is in a very imperative, and I would argue quite unhelpful way. So here's an example of that. So what I've got here are two different algorithms that from an imperative point of view look very, very similar, but are actually fundamentally different. So why are they superficially similar? Well, if we look at the structure of the code in this sort of imperative algorithmic way of describing the algorithms, they each start with a variable x that's initialized to some value. They each have a for loop, so a loop that iterates. They both involve some drawing of some random variables and some computation. They both involve updating x to get a new value, and they both involve returning x or some simple function of it when the for loop has finished, right? So both of those algorithms have that exact same structure. They both take an x, they thread it through a for loop, they mess with it in the for loop, and they return the result at the end. Okay, so just looking at those algorithms, they look very similar in terms of their structure. So in particular, a compiler looking at those two algorithms would think that they had a very similar structure. But actually, from a computational point of view, these are very different algorithms. So why is that? Well, the one on the left is what we would essentially consider to be a map reduce operation, looking at it at a slightly higher level, whereas the one on the right we would consider to be a fold left operation, when again considered at a slightly higher level. And a map reduce operation is trivially and naturally parallelizable, and a fold left in general is not, and in particular a fold left with a non-associative operation is not. And so that one just isn't parallelizable in the same way. Yeah. So if you describe your algorithm in a sort of slightly higher level, more functional way, it's completely clear which one parallelizes and which one doesn't, and it's completely trivial to parallelize the one that does. But when you describe it in this imperative way, it's not obvious at all. And this, I think, permeates a lot of the way we think about computation, a lot of way that people, certainly in the early days, thought about the development of programming languages. They felt that this way of developing programming languages was very natural because, in fact, it reflects, I think, more closely the way computers actually work. But it's not clear that it's a good or helpful way to build algorithms now today. It's maybe not. So what is functional programming? I've mentioned it several times. Well, let's think about the kinds of things that make them maybe a little bit different to imperative languages. So one thing that most functional programming languages really emphasize is the use of immutable data, pure functions, and higher order functions. So immutable data is a big one. So the idea is that you can give names to things, just like you can in an imperative language, but you wouldn't normally change or mutate the thing that name points at, right? So if you say x is 3, that's fine. X is 3, you can say that. But you can't then say add 1 to x or now make x 5, right? Once x is 3, x is 3, at least in some sense. And so that changes how you have to approach programming. If you think about a lot of the algorithms, a lot of the way we think about algorithms, it involves mutating things. Things like for loops have counters like I that goes from 1 to 10 or whatever, where you can't do that in the same way as in a functional language, not in exactly the same way, because to do that in a typical imperative way, you would add 1 to your counter each time you went through the loop, and you're not really supposed to do that in a functional language. So this immutability does change the way you think about programming. It seems a bit restrictive at first, but once you get the hang of how to avoid mutating things, you really see the benefits of avoiding to mutate things, right? So it seems like a restriction, but it actually frees you to build more complex scalable algorithms, it turns out, but it's a slightly subtle thing. Pure functions are functions that don't do anything other than compute a value and return it. So a pure function in the mathematical sense and in the functional programming sense is just something that takes in some inputs, computes a value and returns the value with no other side effects. And so other side effects, of course, might be things like mutating a global variable, right? You're not allowed to do that. It might be things like printing to the screen or writing to a disk or even reading from a disk. Okay, so these are things that we're used to doing in our programs. Of course, at some point we'll have to do some of those side affecting things, but as long as we're careful about controlling them, that's okay as well. But generally speaking, we build our programs using these pure referentially transparent functions that don't have side effects. And again, that really enables us to scale our computation in a way that will be much harder if we were taking a more imperative approach. Similarly, we make a lot of use of higher order functions. So a higher order function is a function that can take a function as an argument or return a function as a value from a function. And they're very powerful, and we use them a lot. Okay, so where does this kind of language live on the spectrum of languages, if you like? So I think a nice way to think about where languages lie is that imperative languages we tend to think of as being more like Turing machines, okay, and functional declarative languages we think of as being more like the lambda calculus, right? They're much closer to the lambda calculus. Now, of course, the Church-Turing thesis says that the Turing machine and the lambda calculus have exactly the same expressive power. So none of this is really about the things you can do with a language. You can do things equally well with an imperative language or a functional language. That's really not the issue at all. The issue is kind of how you do things. And this more declarative, descriptive way of describing computations is ultimately more flexible and composable for reasons that we'll explore a little. Now, the original lambda calculus was untyped. That would loosely correspond to a dynamically typed programming language. So a lot of the languages that are currently used for statistical computing, things like R, Python, MATLAB, they're all dynamically typed languages. You don't have to declare the types of your variables. So a functional language, or a reasonably functional language in that sort of vein, would be Lisp. Okay, so Lisp was a very influential, fairly functional language from back in the day that was dynamically typed, and it's been very influential. And as I say, languages like R and Python have been partly influenced by Lisp. But it turns out that having types in your programming language is really very, very valuable. And so there's definitely been a swing in recent years towards strongly typed programming languages. So programming languages where the compiler, at the very least, does know the types of all of your variables or all of your kind of named objects in your program. And that has many, many advantages. It helps a lot with tooling. It helps a lot with compilation. So it helps a lot with debugging. There are all kinds of reasons why ultimately adding types into your code makes your code much better, much less bug-ridden, and much faster and more efficient. The common arguments against having statically typed languages was that it made the languages more verbose because you had to have type annotations everywhere, and that was true and sort of to some extent is true of some statically typed languages. But modern functional statically typed programming languages also have something called type inference. So there are places where you need to specify the types, like in the arguments to functions, for example, perhaps where that would be helpful anyway, just for documenting what the function does. But actually within, say, the main function body, you don't need to annotate anything with its type because it can be inferred by the compiler anyway. So statically typed languages with type inference sort of have the best of both worlds, right? They are not verbose, but the type information is there. The compiler can figure out the type of everything, and that has many advantages to your code. So strongly typed, so statically typed functional programming languages, good examples would be Haskell and Scala, have a lot of advantage over dynamically typed languages. And this really kind of brings home the connection to category theory, because strongly typed languages are more closely related to this notion of lambda calculus called the simply typed lambda calculus. And the simply typed lambda calculus is interesting because it's a canonical example of a mathematical structure called a Cartesian closed category. And so that then brings us the link to category theory. And so ideas from Cartesian closed categories turn out to be very useful in strongly typed functional programming languages that are strongly inspired by the simply typed lambda calculus, right? And so that is really the main source of the connections between functional programming and category theory. Right, so that's kind of interesting. So as we've said, in functional programming, all your state is immutable. You can assign names to things, but you can't change it. Functions are pure and referentially transparent. However, they can be recursive. Yeah, and so this is really how you get around the sort of iteration type problem, is that you actually do recursion rather than iteration. So you can recursively call a function, and at each level of that call, of course, you can call it with a different argument, and so you can use that to solve problems requiring some sort of iteration or walking over a data structure, etc. And so a lot of functional programming has recursion, at least under the hood, although typically it's kind of buried under higher order functions, so you tend not to do a lot of sort of raw writing of recursive functions, but you end up using a lot of higher level functions that do in fact use recursion under the hood. Yeah, and I think we've said higher order functions are also used a lot. Now, languages like R and Python also support higher order functions, and so you will be at least a little bit familiar with the notion of a higher order function, most likely. So I've stated that functional programming languages are somehow much more suitable for modern computer architectures, but I haven't really explained why yet. So why is it? Well, as I have discussed, modern computers are kind of compositional in the nature of their hardware. They have multiple cores, almost certainly. Even your smartphone will almost certainly have multiple cores. Your desktop computer may have multiple processors, and if you're lucky, you may have access to a computing facility consisting of multiple computers. Okay, so computers are kind of built in a hierarchical way as well, and so that is kind of at the essence of why functional languages are better suited. But most people kind of realize now that we need to do some kind of parallel programming to really get the most out of modern computing hardware. And the question is, how do we do that? Well, if you've ever tried parallel programming in imperative programming languages, so I spent several painful years battling with parallel programming in C, and it's very difficult and it's just horrible. So why is it horrible? Well, it turns out that there are all kinds of ways your parallel code can go wrong that you kind of would never think of until you actually started trying to do it. And so it all kind of relates to things like, well, you've got multiple things going on at the same time. So you've got different processes or threads trying to read variables that are being manipulated by other processes and threads. And there's a question of whether you're reading it at the right time or at the wrong time, and whether your threads are synchronized properly, and whether two threads are trying to actually change a variable at the same time, etc. So there are all kinds of ways it can go wrong, but they almost all boil down to the problem of having shared mutable state. There's some kind of state that multiple threads need to know about, and that state can change through time. And not every problem in parallel programming, but the vast majority of problems in parallel programming ultimately boil down to the complications of dealing with shared mutable state. And so then it should be obvious why functional programming languages make parallel programming easier. It's because they don't have mutable state, and so they can't have any shared mutable state, right? If they don't have any mutable state, they can't have any shared mutable state. And so actually just 99% of the problems associated with parallel programming just disappear. You don't have them. And so it's very easy to write parallel code. It's very easy to get it to work. You very often don't have bugs. There could be like fundamental hardware reasons why you don't get much speed up. I mean, it's not total magic, but you can write parallel code very, very simply, very, very easily, in many ways completely automatically without you having to do anything to change your code at all. And it's all because we don't have this shared mutable state. So I emphasize that immutability, it seems a little bit of a weird thing when you first realize that functional programming languages don't like you mutating state. But the benefits are massive, and they're particularly obvious in the context of parallel and concurrent programming. And, it is the case that functional programming languages have become a lot more popular in the last few years. And this is one of the reasons that people are trying to exploit parallelism in one way or another. And people are coming to realize that it is just much easier to exploit modern computing hardware using a functional language. Right, so I do want to just show a few little code snippets. I don't want this to be a language tutorial or anything like that, but it is just helpful to occasionally just look at some snippets of code just to make things a little bit more concrete. So for that purpose, I'm going to use this language called Scala. So I like this language called Scala. I think it's well suited to statistical computing, and it's a nice sort of practical functional programming language. So there are lots of things that are good about it, but most of the things I'm talking about today are not specific to this one particular programming language. It's more about statically typed functional programming languages in general, of which Scala is a good example. Yeah. So let's get started with thinking about functional code. So we often have collections of things. Yeah. So in R, we're used to having lists of things and vectors of things, right? You often have some kind of container that you can store multiple values in. So we're going to say that MT is a collection of type M. So that might be vector, it might be list, it could be lots of other things, and it contains elements of type T. Okay, that's all right. However, what we say is that if this collection has an associated higher order function called map, which is a higher order function because it takes as input a function that maps T's to S's, and then the higher order function returns a new container, M, now containing values of type S, then we call that collection a functor for reasons that will become apparent. So a functor is just a collection, a collection that is a functor is just a collection that supports this map operation. And here's an example. We've got a list of numbers. We map it with a function that doubles those numbers, and we get back a new list of numbers where the numbers are doubled. right? So that's a very simple thing. You've probably seen a function like this in lots of programming languages. It's really not a terribly alien thing, I hope. But that's all we mean by a functor, at least in the context of collections. Yeah. So if it supports a map operation, then it's a functor. If it additionally supports a very closely related function called flat map, in Haskell this function is called bind. It doesn't really matter why at this moment in time, but if it supports this function called flat map, that is another higher order function that takes a function as input, but this one is a function that takes a t to an m of s and then returns you an m of s, then we call that collection a monad. Again, for reasons to become clear. So let's just make sure we know what that means. So if we take a list of numbers and we flat map it with a function that takes a number and returns a list of numbers, then we will get back a list of numbers. And we can see why it's called flat map if we think of what would have happened if we just used map instead of flat map. If we just used map with this same function, that would have worked, but it would have given us back a list of lists. Okay, and so what flat map essentially boils down to is first of all doing a map operation and then flattening the result. Now that might not be how it's implemented, of course, but that's conceptually what it boils down to. And so that's why it's called flat map, at least in Scala. And this doesn't seem like an amazingly powerful idea when you first meet it. It seems very simple, and it seems like a bit weird to bother to call this a weird name like monad. But a collection that supports this flat map operation and a couple of other things, we call a monad. Now, why is that so useful? Well, it's useful because it's allowed us to sort of chain together. It allows us to chain together functions of this form, functions of the form t to m of s. Yeah, and we'll unpack it properly later. But although it looks pretty innocuous when you first meet it, it turns out to be an incredibly kind of powerful and pervasive idea in programming. So let's unpack it now. We're used to the idea of composing functions. If we have a function f that maps an s to a t, a function g that maps a t to a u, and a function h that maps a u to a v, then we know we can compose them, and in Scala we could write it as h compose g compose f, which you would read as h after g after f, or you could write it in Scala or many other languages like this. It takes an s and it maps it to h of g of f of s. Okay, and the result of that will be a new function that we could call hgf that takes an s and maps it to a v. Yeah, it's glued those functions together to create a new function. So that's how regular functions work. That's all fine. But these things I'm calling monadic functions, these are functions that take a type and return a new type wrapped in a container. M, and we're using m because we're thinking of m as being some sort of monad, and g, which takes a t to an m of u, and h, which takes a u to an m of v. Okay, well, they don't compose directly, yeah, because f gives you an m of t, but g takes in a t, not an m of t, so you can't just compose those together in the normal way. However, if m is a monad, then we're in business because we have this flat map function, and this is exactly what this flat map function does. So s can say, okay, let's start off with f of s, that's now a monad, but that's okay, I can flat map that with g, and I can flat map that with h, and I'm going to get back a function that takes an s and gives me an m of v. So this flat map operation is important because it allows us to compose together functions like these, and these are so-called monadic functions, or functions returning values in a monadic context, and this crops up everywhere in programming, and so the ability to chain these things together is super important, and so that is really why monads are so important. Okay, so this idea of flat mapping seems very simple, doesn't necessarily seem super interesting at first, but it turns out to be really quite fundamental to the nature of computation and just crops up everywhere. And in fact, it's so important that in some languages there's actually built-in language support for working with these kinds of operations, where you don't have to write out big long chains of flat maps. You actually have nice what you might call syntactic sugar for doing these flat maps, writing out your flat map chains in a way that looks a little bit more imperative, in fact, just to look a little bit more familiar to people. So for example, this chain of flat maps up here could be written in Scala as S goes to 4, and this is a for expression or for comprehension. It's not the same as a for loop in an imperative language. It's called for because it's going to look a little bit like a for loop. Yeah. So our for expression says pull a t out of f of s, then pull a u out of g of t, then pull a v out of h of u, and give me back the v. Okay. So that's intuitively what we think of when we think of this set of flat maps here. This expression here, when you write it in the language, just gets compiled down in a very early compiler pass to be exactly this set of flat maps, right? So this isn't an imperative for loop. It's nothing to do with it. You're not really pulling t's out and u's out, right? You're really just translating this this syntax into this chaining together of monadic functions using flat map. Okay, and there's a similar thing in Haskell. In Haskell, it's called do notation, but again, it's because we just end up working with monads a lot, and we end up chaining monadic functions together a lot, and so having some syntactic support in the language for doing this turns out to be very, very useful indeed. And we'll see an example of how we can use this syntax to essentially give us a DSL, a domain-specific language for probabilistic programming for free, right? Just because we're so used to chaining monads together that if the monads we chain together happen to be probability distributions, then what we have is basically a probabilistic programming language. But we'll come back to that later. So what other kinds of monads are there? Are collections the only monads that we have? Well, no, absolutely not. So I'm just going to give you a couple of other examples, but in some sense, most monads are not collections, yeah? But they crop up a lot in statistics, of course, because we're used to dealing with collections of data in statistics, so it's good to understand that type of monad sort of first, but it's also worth understanding that they're not necessarily the only type of monad and not even necessarily typical. So a good example of a monad would be a future. So a future t is sort of a container for a value of type t, but it's a container for a value of type t that might not exist yet. Okay, so a future t is used to basically dispatch some kind of computation, often a long-running computation, to another thread to run in parallel with the main thread of your program. So when you create this future containing some computation that will eventually return a t, your call returns immediately, right? So you don't wait to compute the t and then return the future. You just create the future. That computation of the future gets dispatched to another thread, but your main thread returns immediately, so your program can continue. So you don't have to wait for the future, right? You will get back this value in the future, hence the name, but your calling thread returns immediately and can continue. So that means that you can do things with this future possibly before the value of type t exists, yeah? Because it's gone off to do this big computation that will eventually return you a t, but your main thread is continuing, so you will hold a reference to this future, but the value t that it's computing might not be available yet, which is kind of interesting. But if you think about it, that doesn't mean that you can't map it. Yeah. So if you map a future, so future's a functor, then that transforms the future. And really what it means is that when the t is available, apply this function and, that's going to be my new future. Yeah. So your new future is wait for the old future to finish and then apply this function to it and then return that result as the result of this new future. Yeah, so you can map them, and that would be a way of transforming a future to a different future. And similarly, flat map can be used to chain together futures. Yeah. So you've got a future, and then you've also got a function that returns a future. Well, you can chain those together in just the same way and return the result in a future. And that future, basically waits for the result of the first one, then passes it into the second one, which again gives you back another future, and you wait for that one to complete, and then you get back that value. So you can chain futures together using map and flat map. And ultimately, of course, you're going to want the value, and you're going to need some way of checking whether the value is available or doing something when the value becomes available. But you can create futures and manipulate them using map and flat map immediately without waiting for anything. And map and flat map are, of course, the defining characteristics of a monad. And this turns out to be a really nice, elegant, and powerful way of developing parallel and concurrent codes in functional programming languages. By no means the only way, but it's a basic way that we can create parallel programs in a sort of safe and scalable way. I'm going to come back to this one later, because it's kind of so fundamental in a sense. But again, just to flash up the idea of a monad that isn't a collection, a probability distribution forms a monad. And so in the most basic case, you can imagine, and many programming languages sort of do this, having the notion of a rand t being some kind of random variable that encapsulates values of type t. Yeah, so a rand int would be a random integer of some sort. A rand double would be a random of double precision floating point numbers that you might use to model a continuous probability distribution, for example. But it's not a draw from that distribution or anything like that. It just represents the distribution itself. You might be able to draw from it. You might be able to evaluate its probabilities. There are lots of things you might be able to do with this rand t object. Yeah, but it is in some sense encapsulating the notion of a probability distribution. But if you think about it, if you've got a probability distribution and you apply map to it, you're going to get back another probability distribution. Yeah, that's just transforming a probability distribution. And if you think about it a bit more, this flat map higher order function allows you to chain together stochastic functions. So you take one random variable and you transform it with a function that takes a value to a random variable. So that's like a conditional distribution. So you're sort of coupling together a marginal with a conditional to get a joint that you then kind of sample or something to get values from the either the marginal of the second variable or the joint distribution, etc. So it's a way of chaining together conditional distributions, or to propagate uncertainty through computational workflows or pipelines. Yeah. So again, you can define map and flat map in a sensible way for random variables. So they form monads as well, and in fact, they form the basis for the development of nice functional probabilistic programming languages that we'll look at a bit later. But again, for now, I just wanted to flash it up as not all monads are collections. But some are, and obviously in statistics we're often working with data sets, and so they are important in the context of statistics, but it's worth kind of seeing how they allow us to do parallel computing trivially. Yeah. So how do they allow us to do parallel computing trivially? Well, you can just have a collection that is a parallel collection as opposed to a serial collection. So if you think about it, if you've got a collection of values and you apply map to it, and you're applying a pure function, of course, because again, we're in a pure functional programming language, you don't actually have to do that sequentially, right? You don't have to start with the first element, apply the mapping function to the first element, and then the second element, and then the third. You can do those all completely independently or in parallel. And if you then had an infinite parallel computer, right, so you have more processors than you have data points, then it's clear that if your collection contains n elements, then doing it sequentially would be an order n operation, because you'd have to walk through that list, going through all n elements. But if you can do one element on each processor, because you've got a surplus of processors, then this becomes an order 1 operation. Yeah. So in principle, if you have sort of infinite parallel computing capacity, a map operation can be done in parallel, taking what would be an order n operation and making it an order 1 operation. So that's like a great example of a fantastically parallelizable operation. And again, to see how this might work in Scala, you take your collection of numbers, not a very big collection here, and you map it, say, with a doubling function, you get back a new collection, right? That will by default be done in series. So the algorithm will literally walk through this first vector, apply the doubling to the first element, the doubling to the second element, the doubling to the third element, and give you back your new vector. But you can have parallel collections in Scala as well. And so if you say, actually, make this collection parallel, now map it with a double function. Now this parallel vector will be created in parallel. And so in parallel, this doubling function will be applied to each of these elements, and the results will be stitched back together to give you the result of the doubling. Okay, so this will happen in parallel, but without you really fundamentally changing your code. You've put a .par here to convert this vector to parallel, but otherwise your code is identical. And this is the point that for operations that parallelize nicely, because of the way we structure our codes in functional languages, we can often get the parallelism for free because we don't have to worry about things like shared mutable state, right? We know that these things are immutable. We know that we're applying a pure function, and because of that, we know it's safe to do this operation in parallel. In an imperative language, there'll be all kinds of things you'd have to worry about and check before you knew that this was a safe or reasonable thing to do. But in a functional language, you know you're dealing with a mutable state, you know you're applying pure functions, and so you know these things are safe to do in parallel, and so just do them. Yeah, don't make a fuss about it, just do them. Okay, so map operations can be done in parallel on collections, so that's great. What about other sorts of operations? So we very often also want to summarize data, and we summarize data using maybe reductions or folds over collections. So an example of that would be something like reduce using plus. So that just means add all of the numbers in the collection together and give you the result. Now, can that be done in parallel? Well, actually it can, but you have to be a little bit careful here because not all sequential folds can be parallelized, but some can, and we can characterize very easily those that can, and we can highlight those and use them in our reduction operations. So for that, you really want the concept of a monoid. So what is a monoid? Well, it's the kind of thing that often gets glossed over in elementary abstract algebra courses because it lives somewhere between a semigroup and a group. Yeah, so you can either think of it as being a semigroup with an identity, or you can think of it as a group without an inverse. Right, that's where it lives. Okay, so it's just a closed binary relation that is associative and also has an identity element. Okay, that's a monoid, and that turns out to be super important in category theory and in functional programming, and it's a concept we make a lot of use of in functional programming. And so essentially, reductions involving folds over monoids can be done in parallel using tree reduction, right? Because of the associativity, that's the point. Yeah. If you don't have associativity, then folding from the left might be different from folding from the right, might be different from propagating up a tree. But if you know the operation is associative, then you know you can sort of bracket it any way you like. And so, yeah, you can just arrange all of your elements in a tree, a binary tree, and then propagate up from the bottom, add the pairs at the bottom, then add those pairs, then add those pairs until you get to the top and you've added up everything. But that's now a propagation that's been done depending on the height of the tree. The height of the tree will be log 2 of n, and so you've gone from an order n operation to an order log n operation, again, assuming you've got plenty of processors. So it's not as good as going from order n to order 1, but it's the next best thing, right? So doing an operation in order log n is an awful lot better in doing it in order n. Yeah. So as long as you've got this monoidal structure, this notion of an associative operation, then you can do reduction operations in parallel using this notion of tree reduction. And if you've ever heard of this idea of MapReduce, okay, so Well, it was popularized by this system called Hadoop a number of years ago, which was a Java big data processing framework. So MapReduce is basically just this process. You split your data up into across a cluster. You know that you can do a map operation in parallel. We've just discussed that. And we know that an associative reduction can be done in parallel and using tree reduction. And so that is what we mean by a MapReduce job. And so that is one example of a functional pattern that is used to do big data processing in parallel. And the reason it works is because it's just a standard functional pattern that we know parallelizes. There are lots of other patterns that we can exploit in functional programming, but that's just one example of a pattern that became very popular because it's a standard kind of operation that you want to do a lot of the time when you have a lot of data. You want to transform the data and then you want to summarize it. Yeah, so that's your map and you reduce. It crops up a lot, and so having some kind of support for that seems like a good idea. So these parallel collections can be used in all kinds of ways. So here's a standard example from statistical computing, which is that you've got a load of data, maybe a big data set, and you need to calculate the log likelihood associated with that data set. But actually, you can just write your log likelihood function. So it's completely agnostic to whether your data is held in a regular collection or a parallel collection. So the code that you write is just the simple code that you would always write. However, it will automatically parallelize if you pass in a parallel collection. So how does that work? Well, you can think about having a little function to work out the log likelihood of your ith observation. So there you've got your parameter vector, you've got your observation, and you're going to return a double, which is the log likelihood. So obviously that will be problem dependent what that function looks like, but that's just going to evaluate the log likelihood associated with an observation. So it might be, a log Gaussian likelihood or whatever, it doesn't matter. Right, so your log likelihood function is going to take in some generic sequence or collection of observations. And we don't care whether it's a serial collection, we don't care whether it's a parallel collection, we're just going to take in some collection of observations. We want the parameter vector at which to evaluate this likelihood, and we're going to give back the log likelihood. But our implementation is now very simple. We take this collection X, we map it with a log likelihood function, and then we reduce the result using plus. So assuming IID observations, that is a generic implementation of the log likelihood that doesn't care whether your collection is parallel or serial, but if your collection is parallel, then map can happen in parallel and reduce can happen in parallel. So this function is completely parallelization agnostic. If you pass in a parallel collection, it will evaluate in parallel. If you pass in a serial collection, it will evaluate in serially. That's just it. And so this is just an example of how you don't have to worry about writing parallel code, right? Your code kind of just parallelizes itself if you're using a language with good support. So you can take this idea and really scale it up. So parallel collections are sort of part of the Scala standard library, and they will parallelize operations on multiple cores and processors on a single machine, but they won't automatically distribute your computation on a huge cluster in the cloud, for example. But there are libraries to do that. So you may have heard of Apache Spark. Well, that's just a Scala library that gives you a lazy distributed parallel collection. Okay, so what do we mean by that? Well, it's just a Scala library, and it's meant for doing big data analytics on big clusters of machines in the cloud. So you have a huge data set, you don't want to store it and process it all on one machine, you want to distribute the data across a bunch of machines and spread out any computation and processing of that data across that big cluster of machines. But your basic programming construct is something called an RDD, a resilient distributed data set. But all that is a lazy distributed parallel monadic collection. So it's just like the parallel monadic collection we've just been looking at, except that it supports distribution of data across a cluster, and it's lazy. And we'll come back to why this laziness is handy here a bit later, but it's lazy as well. So what that means is it doesn't eagerly evaluate operations that you do on these RDDs. It waits until you kind of need the result before it actually triggers doing the computation, and there are some advantages to that. But yeah, it's just a lazy distributed parallel monadic collection, and so you program with it the way you program with any other collection. Yeah, you can map it to transform the data, you can flat map it to kind of chain dataset operations together, you can reduce it with reduction operations, and again, as long as that's an associative operation, then that tree reduction can happen in parallel as well. And so your code just looks more or less exactly the same as your regular Scala code looks, right? And it doesn't matter whether your RDD is just a little data set sat on your laptop or it's terabytes distributed over a big Spark cluster. All of the distribution and parallelization and aggregation and everything all just happens automatically. It's all taken care of by the libraries. Your code is very simple and doesn't need to know or care about any of that stuff. It all just happens. And just to mention in passing that these kinds of frameworks are very much intended for processing huge amounts of data, but you don't only have to use them for that. It's actually just a way of distributing computation. And so even if you don't have a huge data set, if you have a big computational problem, then you can actually use exactly this same mechanism for distributing your computation across a big cluster. So again, it gives you a very simple and elegant way to write distributed parallel algorithms that will run across big clusters in the cloud without you having to, do a lot of programming. Yeah, so it's a nice way for thinking about developing scalable computational algorithms as well as distributed data processing. So I keep mentioning category theory and how these ideas come from category theory, and I've talked about functors and monads and their names that come from category theory. So what is category theory and what's it got to do with programming? We ought to just make that somewhat clear. Well, a category is really just a collection of objects and arrows that we call morphisms. And each morphism is, well, an arrow, just an ordered pair of objects. So when you start thinking about categories, it's quite helpful just to start with a picture of a directed graph. Probably you're familiar with directed graphs from other parts of mathematics. That's not a bad picture to start with. Unfortunately, it's not a perfect picture either, as you'll very quickly see, but it's a good starting point. So you just got objects and arrows. One way in which it's not like directed graphs is that these arrows, these morphisms, have to be closed under composition. Okay, so what does that mean? Well, it means that if there exists an arrow F going from object X to object Y, and there exists another arrow G going from object Y to object Z, then there has to be an arrow H going from an arrow H going from X to Z that we write as the composition of G and F. Yeah, and so this is where compositionality comes into the basic definition of a category, right? And so this is why it's in some sense the mathematics of composition, because it's absolutely baked in the very first definition of what it means to be a category is that your arrows have to compose. There has to be this notion of composition, and better still, this composition has to be associative. And we've seen already why associativity is important, right? It allows us to do things in parallel. Okay, so associativity is very important, and again, baked into the very definition of a category is that this composition of arrows that we've just talked about has to be associative, right? So what that means is that if you've got arrows F, G, and H that are all composable, it has to be the case that if you take G compose H and compose it with F, it's exactly the same as taking H and composing it with F compose G, and they have to be the same arrow. Yeah, so that gives us composition and associativity, as a defining property of a category. So, some structure that didn't have these properties would not be a category. But then what that means is that whenever we're working with categories, we've got this very strong notion of associative composition baked in the very kind of foundations of what it means to be a category. And that's why in many ways category theory is about the mathematics of composition. Incidentally, we also need an identity morphism. Okay, so the identity morphism is just an arrow from an object to itself, and it has this property that when you compose it with other arrows, it doesn't change them. Yeah, so we have an identity and associativity, and so you can see that this is actually quite like the definition of a monoid, and this is why monoids are so important in category theory and functional programming, because this monoidal structure again crops up again and again throughout category theory and in fact throughout functional programming. So what are some examples of categories? Well, a good example of a category is the category set, and so that has for its objects sets, and its morphisms represent set functions, right? So you can see how this is another way in which categories are not really exactly like directed graphs, right? Because you can see that there are obviously infinitely many sets, so there are infinitely many objects here. And even in cases where you didn't have infinitely many objects, you will very often have infinitely many arrows, just because you can always compose arrows to get new arrows, yeah? So often, even if you've got a finite set of objects, you'll still have an infinite set of arrows because of all of the compositions you can make, right? So categories are often very big, they're often infinite, and so, yeah, that makes them not so much like finite directed graphs that you're maybe more used to. Okay, so that's interesting because that's very like a programming language, yeah, where we have types and functions, and our types sort of represent collections of things, yeah. So a type integer is basically the set of all integers. The type string is basically the set of all strings, and if we have a function from, say, strings to integers, then that's a function, that's an arrow that takes a string and gives us an integer, and so it kind of gives us an association between all of the possible strings and the resulting integers that correspond to the length of that string. So the category set is very much like the category of types and functions. Now, it's often, worth making a distinction between the two, and so in programming, this one often goes by the name of Hask, coming from Haskell, the programming language. But to a first approximation, these categories are the same, and it often makes sense just to think in terms of set. And in functional programming, we often just think that the category of types and functions that we, have in our functional programming language is just the category set, and roughly to a first approximation it is. Okay, so this is the correspondence between our programming language and category theory, that the types in our programming languages we think of as objects in a category, and any function from one type to another type we think of as a morphism in a category, and that's where the correspondence comes from. And this category set is a good example, probably the canonical example of a Cartesian closed category. And again, we're not going to get into what that means, but it's the main source of the connections between category theory and the ideas and concepts we use in functional programming. So I've talked about a functor in programming. What is it in category theory? Well, it looks a bit more complicated in category theory, because in general, a functor in category theory is a mapping between categories. Okay, so a functor F is a mapping from category C to category D. And what does that mapping do? Well, first of all, it maps the objects. So it has some way of associating with each object in C an object in D. And then it also has to map the morphisms across. Okay, so for each arrow in C, it gets mapped to an arrow in D, but it has to be done in a consistent way. Okay, so what do we mean by that? Well, the arrow x to y gets mapped to an arrow from f of x to f of y. Okay, and so And there were consistency requirements that we need. And so in particular, the identity arrow must get mapped across in the obvious way. But the more subtle thing that we need is that if you've got the composition of two arrows in C, then this must get mapped to the composition of their image under F. Okay, and this goes by the name of map fusion. It's just a basic consistency requirement, and when you actually unpack it, it's pretty straightforward and kind of natural, and it's clear that why you would want it and why it'd be weird if you didn't have it. But it goes by the name of map fusion, and we'll see the implications of that in functional programming shortly. Now, in functional programming, as we've said, we're nearly always thinking about this category set, or Hask if you prefer. And so we're nearly always thinking of functors on set. That is a functor from set to set. And a functor from a category to itself is called an ender functor. So when we say functor in programming, we're really typically thinking about an ender functor from the category of types and functions to itself. Now, the reason that many people consider category theory to be a very difficult and abstract subject is because it gets very abstract very quickly. So a category is already an abstract thing. We've just seen that a functor is a mapping between categories, so that's an even more abstract thing. And now we're going to introduce the notion of a natural transformation, which is a mapping between functors, okay? And so that's even more abstract, right? And so the abstraction really ramps up very quickly in category theory, and it is a bit of a problem when you first start trying to get your head around it. But these are all very kind of elementary, natural ideas that have very obvious kind of translations into functional programming and are very useful notions in functional programming. And so actually by seeing them used in functional programming, you get a feeling for what they actually are really quite quickly, even though the mathematical definitions are really quite abstract. So as I said, a natural transformation is a mapping between functors, and so the details don't really matter. So I'm actually just going to gloss over it here. But we can think of it, because it's a mapping between functors, and we've seen that functors are kind of like containers that can be mapped. And so really a natural transformation is just switching a container. Yeah. So if we had I haven't explained exactly what an option is, but it's a monad. It can either contain a value or not. And a list we have seen. And so you can switch a container if you've got an option, right? There's either a value there or not, and so you can turn that into a list that either has one element or it doesn't, in a very obvious way. And that very obvious way is actually called a natural transformation. Okay, and it's a natural transformation because it satisfies this naturality law. But really all that naturality law says is you switch the container and don't mess with any values it might contain, right? Which is a perfectly natural thing, hence the name, right? So all of this stuff looks a bit abstract when you first meet it, but it all actually corresponds to very concrete and sensible ideas when you translate it back into, say, functional programming, or indeed other areas of mathematics. Okay, so natural transformations are just about switching containers. The reason I have bothered to introduce them here is just that they crop up in the definition of a monad, which again looks quite intimidating when you first see the formal mathematical definition, but again, just kind of squint at it and don't worry about the details. So essentially, a monad is an ender functor from C to C, right? So it's first of all, it's a functor, but it has this additional property, remember, that we just said was flat map, where it actually has another property as well, which is that you can put values into the monad, right? So starting with a plain value t, you can inject it into the monad to get an m of t. Okay, so this is encapsulated through this so-called unit natural transformation, which is a mapping from, well, this is actually the identity ender functor on the category C, which is just the functor that maps objects to themselves and morphisms to themselves. Yeah, it doesn't do anything. Yeah. So, but the idea is it can take values and inject them into the monad. So you start off with a plain value and you get a value wrapped in a context. But the key thing that we mentioned was it had this flat map operation that we could in fact split as a map and a flattening. And in fact, in the mathematical definition, you usually define just this flattening operation. So this just corresponds to flattening. So remember, we could flatten a list of lists down to a list in a natural way. That's encapsulated by this so-called multiplication function because it takes a t cross t and gives a t. That's why it has that name. But this is just our flattening operation. So we've got a way of kind of injecting a value into the monad, and we've got a way of flattening multiple layers of the monad down to a single layer. And that's it. There are some consistency laws, but these consistency laws are, again, very natural when you translate them back into functional programming. So the associativity law just says, well, the two ways of flattening this t of t to a t are the same. So that is, you could flatten the inner two t's and then flatten the result with a t. Okay, that would give you a t. Or you could flatten the outer two t's and then flatten the result with the inner t. And that would give you a t. And those two ways are the same. Yeah. So if you had a list of x's, then the two different ways of flattening that would give you the same result, which it obviously does. Okay. And the identity law that just says if you start with a t of x, well, you can inject it into the monad. Okay, so you could either take that t of x and inject it into the monad to get a t of x, or you could take the x that's inside the t and inject that into the monad to get a t of x. If you were to do that, you wouldn't get the same thing in general. However, if you then took that and flattened it back to a t of x, then you would get back to the original t of x that you started with. Yeah, so if you lift and then flatten, you will get back to the same t. In functional programming, we very often use M for monad rather than T, so the T is a historical thing. It corresponds to a triple. And we will often say there are three monad laws because we'll think of this identity law as being two separate laws. But otherwise, the functional programming notion is essentially the same thing. So we said that monads are really super important because they allow us to chain together monadic functions, or functions returning values in a monadic context. In category theory, this is formalized in something called the Kleisli category. So if we've got a monad T on a category C, then the Kleisli category, we would typically write CT like that. It has the same objects as C, but our morphisms are these funny arrows that return values in a monadic context. So the arrows in this Kleisli category correspond to arrows in the original category of the form x to t of y. Okay, and we define the composition of morphisms in the Kleisli category by doing a map and then a flatten, okay, i.e. flat map. And so this composition in the Kleisli category corresponds to what we've called flat map, what would be called bind in Haskell. And so again, it's just the same idea, just it looks different when you present it mathematically. In functional programming, we sometimes use these morphisms directly. In that context, we call them Kleisli arrows, or sometimes just Kleisli. Occasionally, people just refer to them as arrows, though that's slightly confusing because arrow can mean different things in functional programming. But yeah, Kleislis or Kleisli arrows do crop up in functional programming, but they're just these functions that return values in a monadic context that you want to chain together, in principle using flat map. But if you think of them as Kleislis, then it's just the actual composition definition of two Kleislis. As if that isn't all abstract enough, almost every concept in category theory has a so-called categorical dual, and the duals nearly always named by sticking a co in front, right? So the dual of a monad is a comonad, and duals are typically formed by just taking the original concept and switching all of the arrows around. Okay, so we get a comonad by taking the definition of a monad and then switching all the arrows around and seeing what that gives us. And it gives us something called a comonad. So remember, we had two natural transformations on a monad, one to lift values into the context and the other to flatten. So on a comonad, we have the opposite. For a comonad, we have so-called co-unit, often called extract, because it extracts a value out of the monad. So if we've got something in a monadic context, we can strip off the monadic context to get a single value. And similarly, if we've got something in a monadic context, we can wrap another layer of monadic context around it, and that's called duplication often, or co-multiplication. And we have the corresponding laws, and again, the laws say the obvious thing. So, the associativity law says, well, you can duplicate a wx to a ww of x. There are clearly two ways of doing that, and the two different ways of doing it will end up with the same thing. Similarly, the identity law says that if you extract a value from that, or you extract a value from a duplicated, then you end up with the same thing. Yeah. So it's just the dual of a monad, right? This doesn't tell us why it's useful in computing, right? So we've seen a few examples of why monads are useful in computing. Does the comonad correspond to something useful in computing? Well, it does, and it's actually particularly useful in statistical computing. It's actually a very natural way of capturing a very commonly encountered class of algorithms in statistical computing. But we'll illustrate that in a second. Before we kind of get sidetracked by that, I wanted to come back to this issue of these laws, these category theory laws that are required to hold, because they actually have important ramifications in computing as well. And so to see an example of that, let's go back to a Spark RDD, right? So we said that Spark had these lazy distributed data sets. We could take an RDD, we could transform it by mapping it with a function f, we could transform it again by mapping it with a function g, and then we could reduce the result to get a value. Yeah, so that would be a typical example of a computational pipeline in Spark. And at the end, we'll get a value of type v. However, what we're doing here is we're first mapping with f and then mapping with g. So in principle, there's a sort of intermediate collection here that we don't really need, which is the result of mapping with f. Right? We don't ever need that because we're just going to map it with g to get another collection, and then that's the one we're going to reduce. Okay. So in fact, we could rewrite this as, let's take the RDD and map it with a composition of g and f, and then reduce the result. And it's pretty obvious if you think about these two definitions that these are the same thing. However, it's more fundamental than that, because what we're saying here is that these two things are the same thing, and these two things are the same thing because you can fuse together these two maps into a single map operation, and that corresponds precisely to that second functor law that I said was called map fusion, right? So you see now why it's called map fusion, because it's just fusing together two maps into a single map. Now, this is interesting in its own right, but it's a sort of an example of a more general principle, which is that these category theory laws typically correspond to ways of rewriting your code that you know are identical, yeah, that they are logically identical. And so sometimes when you apply one of those rewrites that you know won't change the meaning of your code, sometimes they will correspond to slightly more efficient ways to do the computation, right? As it does here, right? So it saves creating this intermediate collection, so this will nearly always be faster, even though the results will be the same. Yeah, and so often you can rewrite your code using these category theory laws, and sometimes those rewrites will correspond to faster, more efficient ways of implementing your code. And so these laws kind of correspond to optimizations that can be done automatically, at least in principle. Now, in regular Scala, this wouldn't happen automatically because Scala is a strict language, and so the way that the language is implemented, you have to do if you do this map f, then it does the map f, and it will do the map g on the result, right? Because it's strictly evaluated, so it kind of has to do this before it does that. But I mentioned that these Spark RDDs are lazy, and this is exactly where the laziness comes in, because Spark can actually just look at this whole thing, and it doesn't actually do anything till it gets to here, and then it says, okay, now now they're really wanting a result, so I better compute a result. But it can look at this whole lazy computational pipeline and say, okay, look, we got a map here and then another map there, but we don't need that intermediate collection, so we can just collapse that using map fusion. And I know that's a safe thing to do because the map fusion law tells me that that's a safe thing to do. Yeah, and so actually what Spark does, Spark would apply this optimization automatically. Yeah, it would fuse these two maps together. It would never build the intermediate collection. Okay, that's possible because of laziness and because Spark is a little bit clever. But this is again an example of a more general principle that we can, in principle, apply optimizations automatically to our code. Using the idea of these self-consistency requirements that come to us from category theory. So when we take these functional programming these category theory concepts and we want to use them in our functional programming code, right? We want to use the fact that this is a functor, right? And we want to use the fact that this is a monad, and we want to write code that is generic, right? So often if we're just mapping and flat mapping, then all we need to know about the thing that we're passing into it is that it's a monad. We don't need to know exactly what monad it is. So if we want to write generic code that is nevertheless safe, then we need some ways of describing this is a monad, this is a functor, this is a comonad, etc. And then we can parameterize our code so that it says, this function will work for any container type W, where W is a comonad. And then we just write our code in a generic way, and it will go away and do that. So to do that, we need a way of encapsulating in code what these things are and what structures they have. And so in Scala, we do that with the notion of a type class, and the type class is encoded with something called a trait. But it illustrates something kind of interesting about sophisticated functional languages with advanced type systems, because if we want to define something like a monoid, we can do that. We can say, okay, a monoid of type A is any type A that has a combine operation where I pass in two A's and I get back another A, and it also has an identity operation where I just get back an A. Yeah, so that describes the basic structure of a monoid. It's a type A that has an identity and a combine operation. Yeah, so far so good. Lots of languages support these kinds of generic types. But now we come to a functor. And what is a functor? Well, a functor is a container type F with the property that it has this map operation where you can take a function A to B and get back an F of B if you start with an F of A. Yeah. However, to encode this as a trait, you need the notion of a generic type whose type parameter can also be a generic type. Yeah. Otherwise, you can't encode this higher level behavior. But this is something called a higher kinded type. So lots of languages support generic types like this monoid at the top here, but very few languages actually properly support this notion of a higher kinded type, where you can have generic types whose type parameters are themselves generic types. And probably actually Scala and Haskell are the only languages you are likely to have heard of that really support these higher kinded types properly. And so that's one reason why functional programmers quite like languages like Scala and Haskell, because it enables you to define these concepts like functor monad and comonad in your type system and use it to write safe generic code. It's hard to do without these type classes. Okay. And here's a comonad as well, which has an extract function, which allows you to get a value out always, and co-flat map, which is the kind of opposite of flat map. So you take a function that takes your entire structure and returns a single value, and then you can apply that over your entire structure to get back a new structure containing B's. And we'll see what that means in a second. So what these generic type classes allow you to do is to write very, very generic code. Yeah. So all you need is just some notion of a generic container for things, and a lot of code you can write in a safe kind of strictly typed way where the compiler knows the types of everything, but your code is not specific to any particular type. So it's not like really strongly constrained, because all you need to know is not what the exact type is when you're writing the code. When you're writing the code, all you need to know is that the type belongs to this generic type class. But when you actually come to use it and the compiler comes to compile your code, then if you actually use that code, you'll use it by passing in a specific type, and your compiler will resolve all of the specific types. And so all of the kind of optimizations can happen, but your code is generic for all types conforming to a particular type class. And so again, it's all about getting the best of both worlds, the best of sort of doing things in a dynamic way, the best of doing things in a static way. You get the best of all worlds if you can work in these strongly typed languages but use generic types. So an example for this would be something like doing ABC, right? So we haven't talked about ABC in the course, but it's a pretty simple idea. You want to do inference for some parameters of a model based on some data. What do? You simulate a bunch of parameters from a prior. You forward simulate your model to get some synthetic data. You compare the synthetic data with the real data, and the parameters that look most like the parameters that lead to synthetic data that looks most like the real data are the ones that you're more likely to keep. And if you do this in just the right way, you can end up with a posterior distribution for your parameters. Okay, how do we do this in a really kind of generic and scalable way? Well, we just have some collection of parameters, and that could be a serial collection, it could be a parallel collection, it could be a Spark RDD. We don't care, okay? But what we care about is that it's monadic, and probably that's about it. So the essential features of your model are that you have some actual data, you have some simulation model that takes a parameter and gives you some synthetic data. You have maybe some summary statistic function that takes your data and gives you a summary statistic. And then you have maybe some sort of distance function that takes two summary statistics and gives you back a distance. Okay, so you need to define these functions, but they'll often be quite simple to define. And then your sort of ABC algorithm is basically just, okay, well, I want the real summary statistics, which are the summary statistics for my real data. And then I just want to take my sample of parameters from the prior distribution. I want to map the result of, first of all, running the simulation model and then computing the summary statistics. And then I want to filter that maybe by the distance being below some threshold. Right? And again, this definition doesn't care what sort of collection this is. It doesn't care whether it's a serial collection, it doesn't care whether it's a parallel collection, it doesn't care whether it's a distributed parallel collection on a massive cluster in the cloud. This algorithm will run exactly the same way. So again, you're writing exactly the same code, not caring whether your algorithm is serial, parallel, or distributed. And it also illustrates the fact that we've used map fusion here to avoid creating the collection of synthetic data sets, and that might be useful because it could be that your synthetic data sets are actually quite big. So avoiding computing directly this intermediate collection containing all of the synthetic data results may be a very important optimization. Okay, so actually kind of hard coding this map fusion into the algorithm is probably a smart thing to do. What about comonads? So I've said they're useful in statistics as well. So they're useful because what they really do is they allow you to take a local computation. So for example, smoothing a few pixels on an image, or smoothing a few values of a time series. Yeah, so that's a local operation. You zoom in on a data structure like an image or a time series, and you apply a local computation to a small number of values of that time series or image. And then you want to smooth the entire time series or the entire image by taking that local computation and applying it all over your time series or your image to get a new time series or image corresponding to the smoothed data, say. Well, whenever you've got that situation where you've got some data structure, you've got some local computation that works on a small aspect of that data structure, and you want to apply that to the entire data structure, that's exactly what comonads solve. That's exactly the problem that they solve. And so you can see that crops up all over the place in statistics, yeah? So doing linear filters on time series and images is a good example, or indeed nonlinear filters. Gibbs samplers have this basic structure that sampling from a full conditional is a local operation, but then you need to sample from all of your full conditionals, so you're taking that local computation and you're extending it to the entire conditional independence graph. So that has the same structure. In machine learning, convolutional neural networks have the same structure as well. So comonads, right, crop up all over the place. Comonadic operations crop up all over the place. So let's just see an example of that. If we think about applying a filter to a stream, we first of all need our local computation. So that says I want to apply a computation to the head of the stream. Yeah. So I'm going to have some weights, and what I want to compute is the weighted sum of the first few values of that stream. Yeah. And the details don't matter, but here's the function that does it. But the point is that I pass in a stream, and I'm going to get back a double, which is the result of applying that operation to the first few values of that stream. What I then want to do is smooth the entire stream by first of all applying it to the head of the stream, then discarding the first element, taking the rest of the stream, applying it to the rest of it, discard the head, apply it to the rest, discard the head, apply it to the rest, and I get a new stream. Now, another slightly curious thing, if you're not used to functional programming, is that there's no problem with that stream being infinite, right? So this can be an infinite stream, that's no big deal. In functional languages that have some kind of support for laziness, we work with infinite data structures all of the time. As long as you don't try and compute the entire data structure at once, then there's no problem working with infinite data structures, though I don't have time to get into the details here now. But the idea is we just take this function that does this local computation and we co-flat map it over the entire data structure, and we get back a new data structure containing the filtered results. We do the same thing with an image, but the difference here is that we need some kind of cursor, right? We have to have this extract function. This is in the definition of a comonad. We have to be able to call extract and get back a value. For a stream, it's obvious what that should be. It should be the head of the stream. Yeah, so if you call extract on a stream, you get back the head of the stream, the first element of the stream. But for an image, it's not clear what you should get back. And so what you actually do is you work with a so-called pointed data structure, which is your data structure, like your image, together with a cursor that says what my current location is. And then you have functions that shift the position of that cursor, say up, down, left, or right, and give you back a new image with a cursor at the new location. So then you can use that to define local computations. So here's a simple smoothing function that basically just says, okay, I'm going to take my pointed image. Okay, so pi here is for pointed image. I'm going to extract the value where I am now, but then I'm also going to move up and extract the value, down and extract the value, left and extract the value, right and extract the value, and I'm going to weight those together in a sensible way to give me a locally smoothed average of that local part of the image. But that is going to just do that for the location that I first started from. Yeah, so wherever the cursor was pointing to start with, I then call this function on it and I get the smoothed value at that location that the cursor was pointing at. But I now want to take this local computation and apply it to the whole image. Well, I do that using co-flat map. Okay, and that's how you'd smooth the whole image. And then you could even create an infinite stream of smoothed images where you apply it again and again and again to make it smoother and smoother and smoother. Again, the details don't matter, but it's just comonads encapsulate this idea of taking a local computation and applying it to a big data structure, and that is the kind of operation that crops up a lot in statistical computing. We've also talked about things like folds and reduction operations, and when reduction operations are parallelizable and that sort of thing. It turns out that, again, there are connections with category theory, and so this notion of a fold is sort of a special case of a more generic reduction type operation called a catamorphism. The idea of generating an infinite stream is an example of an unfold operation that, again, in category theory might be called an anamorphism. If you think about doing something like MCMC, where you generate an MCMC chain and then compute some summary statistics of that chain, you could do that by first generating the chain and then consuming it, or you could actually compute the summary statistics on the fly and not store the entire chain. If you did that, that would be what's known as a refold in functional programming, or a hylomorphism in category theory. And there's all sorts of like mathematical structure here that you can kind of use and exploit to better understand the properties of these algorithms. So a lot of the algorithms that we use in statistics are just special cases of these more generic concepts that are well understood in mathematics and in functional programming. And so a lot of the things that we do, we're often just making things up as we go along, but in fact their computational structure is well known and well understood, and we're always just reinventing ideas that already exist, and it's helpful often to understand that our algorithms are actually of a very standard, well-studied form, and their properties are well known and well understood, and we can use those properties and use ideas to help us, maybe improve our algorithms and modify them in ways that make them more scalable, for example. So there's loads of theory out there that we can borrow on, and it's quite insightful to understand how a lot of these statistical algorithms that we've kind of studied in their own right, in their own context, we've not really thought of as being general sort of algorithmic and computational patterns, actually conform to very standard algorithmic and computational patterns. And understanding that relationship, I think, can be very helpful in lots of ways. So we've so far talked a lot about doing computation scalably. We've not really talked so much about doing modeling scalably. But if you think about it, in statistics, we're often interested in building big, complicated statistical models, right? We're not just interested in, building big matrices and doing big computations over big data sets. We actually often these days want to build large, complex models. And actually that process of building large complex models is itself problematic and error prone, and again is not well supported by the programming languages that we typically use. And so it's worth just thinking about that problem now. So a good example would be things like Bayesian hierarchical modeling, right? That's a really powerful idea. It allows us to describe quite complicated large models, and then we can feed in some data and do some posterior inference, right? So we're used to the idea of probabilistic programming languages, right? You're used to things like bugs, JAGs, STAN, etc. We can describe a model, we can do some computation, and we can get some results. So probabilistic programming languages are becoming quite important in statistical computing. And again, I would argue that there are advantages to thinking differently about probabilistic programming languages from, the way that they're currently envisaged, at least within the statistical community. And again, I'm going to argue that this notion of a monad is really crucial to thinking about how to get this more functional perspective, more compositional perspective on what probabilistic programming is all about. And that, I think, is going to prove helpful in the future. So what about probability monads then? So what is a probability monad? Well, I sort of kind of trailed it much earlier in this lecture. Just as we can have monads for lots of different things, we can have monads for probability distributions as well. And so a probability monad is really just an encapsulation of a probability distribution. Yeah, and we'll skip over the mathematical details shortly, but just think of it as an object representing a probability distribution. So what do we do in probabilistic programming? We take probability distributions and we glue them together to make bigger probability distributions. And what I'm going to argue is that monadic composition is the canonical way to glue together probability distributions to make joint distributions. Yeah. And so that underpins the way we think about doing scalable probabilistic modeling, because scalable probabilistic modeling is all about thinking about how to glue together random variables to make bigger models. Okay, So let's just make sure we can walk before we start to run. So let's just think about something really, really simple, like an exponential mixture of Poissons, right? Where we're just gluing together two probability distributions. So if we do that, we first of all need a notion of an exponential distribution. So we could think of exponential as being a function that takes a double, representing the rate of the exponential, and then returns us a probability distribution, and that represents the exponential distribution with that particular parameter. And similarly, we could think of the Poisson distribution as a function which takes in a double, representing the mean of the Poisson distribution, and returns us back a rand of ints, representing a probability distribution over the integers, corresponding, of course, to a Poisson with the particular mean that we provided. Yeah. So the exponential and the Poisson distributions are functions of one real input. They don't compose. So we're trying to glue together this exponential and Poisson. They don't, because the output of exponential is a rand double, the input to Poisson is a double. They are not the same type, so those two functions don't compose together in the usual way. But by now you should know what's coming, which is that they don't compose together directly, but they do in the Kleisli category of the rand monad, or in other words, we can take our exponential 3, say, and we can flat map it with a Poisson, and that will give us back a rand int, which will be a random variable representing this exponential mixture of Poissons, which in fact will be essentially negative binomial, but that's not important. We've glued together these two probability distributions to get a new probability distribution whose marginal is this exponential mixture of Poissons. Yeah, and so flat map is the key to gluing together these two conditional distributions. That's the big insight as to why probability monads are useful for building probabilistic programs. So I've mentioned how 4 expressions or 4 comprehensions can be used to sort of hide some of the details of chaining together lots of things using flat map, and to write those chained flat maps in a slightly more friendly and intuitive, possibly even imperative way. So here's an example of that. So this is just a standard Scala 4 comprehension. This isn't some probabilistic programming language that we've invented. This is just standard Scala syntax where we would write our 4 expression like this. So we could say, okay, mu is going to be a Gaussian, tau is going to be a gamma. I'm going to let sig be some transformation of tau. Then I'm going to define obs to be a Gaussian with parameters mu and sigma, and I'm going to return the joint distribution. Okay, but that looks exactly like, or looks very like, a lot of standard probabilistic programming languages, but it isn't, right? This is just basic Scala syntax. It's not some DSL that I've defined. It's just bog standard Scala syntax. You write this kind of code all of the time when you're dealing with monads, so you get this kind of syntax for free whenever you're working with monads. Okay, so these probability distribution objects, it's all about what they really mean. So we've said that they're probability monads, but in the simplest case, these probability monads, they might just give us, say, a draw function that will allow us to forward simulate from these models. And so that's great. We write this probabilistic program here. We'll get a draw method for the result, which will allow us to draw forward samples from this joint distribution. But when we do probabilistic programming, we're normally thinking about doing a little bit more than forward simulation. We're often thinking about doing conditioning and drawing from the resulting posterior distribution. But exactly the same modeling approach can be used. It's just a matter of how you implement the probability monad that changes. Okay, so obviously if we're doing something sophisticated, we might want to use SMC or MCMC or particle MCMC or HMC, and we might want to compose the algorithms together as well. We're not going to say much about that, but again, that's something that we can do. But also, rather than sort of choosing your monad up front and then writing your probabilistic program, it would be nice if you could write your probabilistic program without worrying too much about what the associated probability monad is going to be, and then deciding on that later. And that's what this thing called the free monad allows you to do, right? It allows you to describe the structure of your model independently from its implementation. Yeah, and so again, free monads are a bit of an abstract idea, but they allow you to do exactly that problem. They allow you to defer the implementation of your monad, and there are many possible advantages to you doing that. We'll come back to that later briefly. So mathematically, what is a probability monad? Well, it turns out there are various ways you could define it mathematically. The standard starting point is something called the Dewey monad, and this is basically defined on the category of measurable spaces. Okay, and so it's exactly what you would expect it to be. It's the sort of measure theoretic notion of probability defined on a category, but where your flattening operation corresponds to marginalization in the Lebesgue sense. So if you don't like measure theory notation, you won't like this notation, but it's just saying that flattening is marginalization, and that's exactly what we've seen intuitively already. But the point is that if you set things up this way, then you do get a category and you do get a monad, and that's all great. But what's a bit weird is that this category measure is not Cartesian closed. And I've emphasized all the way along, without ever really explaining what a Cartesian closed category is, that there's a very close correspondence between functional programming languages and Cartesian closed categories. And one of the problems here is that if you do set up your probability monads this way, it's a bit awkward to directly translate this into code, because everything in FP languages is really set up on the assumption that the categories you're working with are Cartesian closed. And so whenever you work with something that isn't like this, there's a little bit of what you might call an impedance mismatch. It just isn't totally natural. And so for various reasons, it would be kind of nicer to have a foundation for probability that was based on Cartesian closed categories. And in fact, this whole research area has been stimulated in recent years, and people have been thinking about exactly this problem, stimulated by the desire for the development of higher order probabilistic programming languages, right? So the problem is that in measure theory, you may know that it's all very well having probability measures defined on measurable spaces, but as soon as you then rack that up to think about defining probability distributions over functions between measurable spaces, then that becomes problematic, right? You can't always do that, certainly not in an automatic way. And so that's where the problem lies. So it would be nice to work with spaces where you could do that. So if you had probability distributions on types, you could also have probability distributions on functions between those types. And there are various ways of kind of rethinking sort of probabilistic foundations and categories and monads for probability that do support that notion. I don't want to get into the details at all, but it's just quite interesting that there are some areas of pure maths that have sort of been stimulated to kind of explore new directions by people exploring functional probabilistic programming languages. I think that's kind of cute. So what about different implementations of probability monads then? The theory is all very well, but in practice you don't have to worry about any of this stuff. You just do it. You define your maps, your flat maps. You make sure it all works. You don't have to worry about the theory very much at all. We've talked already about this notion of a forward simulation monad. So basically your monad, as well as having its flat map operations, it has a draw method, which is some method for drawing a random number from that probability distribution. I've kind of glossed over the whole issue with random numbers in functional programming languages and the complications that there potentially are. There are potentially complications because the way random numbers are often implemented is that there'll be some global mutable state for your random number generator, and every time you draw, you'll mutate that global state, and that doesn't fit very nicely with a functional programming approach. And so you need some tricks to get around that. But again, it's not difficult, but I don't want to get bogged down with the details now. But you have some kind of draw method for drawing from that distribution. And your monadic bind works by saying, okay, if you've got a random variable, you bind it with another random variable. Essentially, you define the draw method on this composed random variable by saying, okay, I'm going to keep a reference to the first one. I'm first of all going to call draw on that first random variable. I'm then going to use that to define my second random variable, and then I'm going to call draw on that, right? And that's your draw method on your flat mapped random variable, okay? So that's how you chain things together, and that's very easy, and it's pretty clear that that is going to work. But that's a very, very simple probability monad, and there's no notion of conditioning here on data. So if you want to be able to condition on data, you probably want some sort of different representation. So one thing you could do is just, instead of a probability distribution just encapsulating a draw method, maybe it could encapsulate an empirical distribution. Yeah, so maybe it could encapsulate a set of draws from that distribution as a set of particles, and maybe those particles could be weighted as well. So maybe it could be a weighted set of particles from a distribution. Okay, and then mapping is easy because you just map all of the particles. Flat mapping is, again, basically the same way you'd flat map collections. Okay, it's just a collection of particles in some sense. There's an issue with your collections getting very big, so you might want some sort of thinning operation. But basically, map and flat map are just as they are for collections. But then it turns out to be easy to define a condition method, which basically just uses important sampling using the observed data likelihood to reweight your particles. So you can then just implement a generic probabilistic programming language with generic conditioning very, very simply and easily. I've got a little blog post where I implement a kind of fully blown generic probabilistic programming language in Scratch, in Scala, in less than 50 lines of code. Yeah. Obviously, this method is not going to be super efficient for complicated problems, right? So you wouldn't use this for real problems necessarily, but it just illustrates the idea that if you can implement your monad, you get the probabilistic programming language for free. So in this case, where it's really easy to define that probability monad, then you get the full-blown probabilistic programming language associated with that monad in very, very few lines of code. More generally, you can put all of your effort into defining the probability monad and its semantics without worrying about how to define your probabilistic programming language, what the syntax should be, how you can parse and interpret that probabilistic programming language, right? All you have to concentrate on is defining the monad and the operations on the monad. If you do that, you then kind of just use your embedded language, right? It's a so-called embedded DSL, where you get the rest of the structure of your probabilistic programming language from your host language without you having to worry about it. So that gives us a nice way of understanding in principle how to develop a probabilistic programming language from scratch. But it's not very efficient for complicated problems. So for more complicated problems, we might want to do something more sophisticated. HMC is very popular for complicated models at the moment, for better or for worse. And we could certainly take that approach to Bayesian inference. So in particular, we could use our probability monad to represent the joint log density of the variables in our problem. And then that's a very easy thing to do, because flat map, if you think about it, is just multiplying your conditional densities together. Conditioning is easy because you just multiply by the likelihood. Okay, so it's actually really simple to define a probability monad based on defining a joint log density of the variables in your problem. And then once you've got that log density, there's the question of how you sample from it. But actually then that's a separate problem. So that's a nice way of sort of defining your model in a modular way, that you have your probability monad in order to allow you to define the log density in a nice, scalable, composable way. The result of that is essentially a function for evaluating the log posterior. And once you've got that function for evaluating the log posterior, you can use whatever algorithm you like. So very simply, you could use a Metropolis-Hastings algorithm. There'd be some question about how you would tune it optimally, but in principle, you could do that quite simply. You could use this approach for doing Gibbs sampling as well, but that would be a bit more complicated because you'd need to keep track of dependencies if you're going to have an at all efficient Gibbs sampler for this sort of model. But if you are wanting to use gradient information because, for example, you're wanting to define some kind of Langevin or HMC algorithm, then you obviously need a way of computing and tracking the gradients associated with that log likelihood. We've seen earlier in the course that automatic differentiation is a good way of doing that. But in the course, what we showed was we could use object-oriented programming ideas in order to kind of hijack our expressions to compute gradients as well as values. Well, similar ideas can be used in functional programming as well. And in fact, again, it all turns out to be sort of monadic. Again, I'm not going to get into the details, but you can do automatic differentiation quite elegantly in functional programming languages too. And in fact, there's a nice little library in Scala called Rainier that does HMC for probabilistic programs in Scala. And so if you're interested, maybe have a quick look at Rainier for how it approaches this problem. So why do this rather than, say, use bugs or JAGs to describe your problems? Well, I'm concentrating right now on the modeling phase, right? So what if I want to build a big complicated model? I can do that in any probabilistic programming language, but it's quite painful to do it in most probabilistic programming languages. And in particular, most probabilistic programming languages that people use are not compositional in the kind of sense that I've been talking about here. And so in particular, what you might want to do is take some small model, say a little regression model for some subset of data that you've got, and kind of use that model and debug and test that model and get that working on a small subset of your problem. And then you want to reuse that component, that probabilistic program, in a bigger model. Yeah, maybe a hierarchical random effects model where you fit data over multiple groups and you borrow some strength across parameters or something. If you think about it, that's really hard to do in the standard languages. So if you think about something like bugs, right? If you took a model and then you wanted to embed that into a bigger model with another layer of hierarchy, you'd end up just copying and pasting the code and kind of hacking a for loop around it and then going through every line of your code looking for the indexes and hacking in an additional index into any array reference you had within your code, right? You can't just take your component and kind of glue it into a bigger model. That's just not the way these languages have been developed, right? Because they haven't been developed with the principle of compositionality as kind of one of their guiding principles for the development of the language. And so by working with an embedded probabilistic programming language, DSL, in a functional programming language, we kind of will get that kind of compositionality just as part of our, one of the many benefits we have from working in that language. And so it will be more compositional. So you will be able to take components and drop them into bigger models in a natural way without, editing any source code. Yeah, so they are compositional in that sense. And so from a modeling point of view, it allows you to build bigger, more complex models in a more principled way than in a language that is not compositional in that sense. I've already hinted at this issue that we might not want to define our model exactly the implementation details of our probability monad and then define our probabilistic program and have that probabilistic program irrevocably coupled to that particular probability monad implementation, we might want to just describe our probabilistic program in a way that would make sense for any sensible probability monad implementation, and then take that probabilistic program and then attach it to some kind of implementation of a probabilistic program probability monad later, and you would call that interpreting the monad. And so you do that using this notion of a free monad, and we're not going to get into the details here, but the point is that you can do this. So you can just define your probabilistic program and then later say, actually, I want to interpret this using an SMC monad, or I want to interpret this using an HMC monad, or a particle MCMC monad, or I want to couple together an SMC monad and an MCMC monad to create a particle MCMC monad, right? You can do this later using this concept of a free monad. The details are not especially important, but just this idea that we can compose and layer together our inference algorithms in the same way that we can compose together our probabilistic program is an important idea, and it's enabled by this idea of a free monad. So Bayesian hierarchical models are a really powerful tool in modern statistical computing. Bayesian graphical models are sort of an attempt at a compositional way of building models. They're not like fully compositional, but they're sort of getting there, right? You can take bits of graph and you can glue the graphs together. So the usual way we think of graphical models, that we're kind of missing the gluing together operations, but it's not too much of a stretch to see how this could be done. And so thinking about graphical models and hierarchical models and how these can be expressed as probabilistic programs is a very natural thing for us to think about. And again, I think thinking of them in the context of probabilistic programming languages and why a functional probabilistic programming language might more naturally give us a compositional way of building these sorts of models, I think makes a lot of sense. And again, as I've hinted at, as well as building our models in a scalable compositional way, we might want to build our inference algorithms in a scalable way as well. And we also might want to automatically parallelize them and things. And so thinking about mapping algorithms to models and doing this in a scalable way is very much kind of state-of-the-art, cutting-edge things that people are thinking about right now. But it's clear that some algorithms sort of naturally represent the compositional structure of the underlying model. So something like a Gibbs sampler, it really does consist of local operations on the conditional independence graph, and that was hence the connection to comonads. So that there the algorithm really naturally decouples with the structure of the underlying model. But not all algorithms do, and so things like a typical HMC sampler, for example, it doesn't really decompose with a model structure very nicely, but it does to some extent decompose over observations, and so you can in some circumstances exploit that as well. So this is all very much sort of at the forefront of what people are thinking about right now, but these are things that people are thinking about right now, and I think it's going to be very interesting to see what happens in this space over the next few years. So I've talked for far too long already. To wrap up then, mathematicians and theoretical computer scientists have been thinking about models of scalable computation for decades, right? And in particular, in the last 4 decades. I think it's probably fair to say that not very much of this thinking has made its way into the languages and libraries that we typically use for scientific and statistical computing. I mean, I'm not saying none of it has, because clearly some of it has, but I think we are a little bit stuck with using ideas and languages from really way back in the dawn of the computing era, and maybe it's time that we took a closer look at some of the things that have happened in the last few decades. I've tried to argue that functional programming languages offer a lot of promise in this regard, and that they are, I think, particularly well suited to many of the things that we do in statistical computing and computational statistics in particular. And I've tried to explain why these ideas from category theory keep cropping up in functional programming and why they're useful, and how they help us to think about the structure of computation and how to organize our code. And then towards the end, I've tried to kind of give a little bit of a flavor of probabilistic programming, which is obviously a sort of a very specific kind of computational statistics, but one that's very important, and why, again, ideas from functional programming and a little bit of category theory give us a nice starting point for thinking about how to develop probabilistic programming languages in a composable and scalable way, and why that might be useful. Okay, and so again, as I've tried to explain, none of this is about, say, Scala in particular. I've said it's a language that I quite like, but the principles are really about strongly typed functional programming languages. And Scala is just one example of that. Really, the principles are very deep, because what it's really about is about actually thinking about algorithms from a categorical perspective. That's really what's underpinning all of this. And so forget about programming languages. If we just think mathematically about how to build probabilistic programs, what I'm arguing is that monadic composition is really the key building block for making probabilistic programs in a composable and scalable way. And so that's how you should be thinking about it, irrespective of what programming language you use. But obviously, if your programming language does have good support for working with monadic variables, then you're obviously going to get a lot of benefits from that, right? It's obviously going to simplify a lot of what you're doing. And so it goes much deeper than kind of the surface syntax of any particular programming language. It's more about changing how we think about how to do computation that is the important thing. So that is it. A few references. I'm not sure there's any I particularly want to pick out, other than if you are interested in the mathematics of the underpinning probability theory and probability monads and different ways of building probability monads, this paper here by Chris Heunen and colleagues is a good place to start. This paper I've got here on arXiv is kind of like a working paper that covers a lot of similar ground to this talk. And this final paper here is a really nice paper about building a modular functional probabilistic programming language in Haskell. Okay, now Haskell I haven't said very much about. It's another very interesting, strongly typed functional programming language, but it's lazy by default. And for that and a few other reasons, I actually think that Scala is probably a little bit better suited to statistical computing than Haskell, but I'm sure that lots of Haskell people would vehemently disagree with me. But either way, it's a very interesting language, and a lot of interesting functional programming research is done first in Haskell, so it's kind of worth knowing about that language kind of irrespective. So that's kind of interesting too. And I sometimes talk about this sort of thing on my blog as well. Okay, so well done. Thank you for making it this far. I wasn't expecting this lecture to go on quite so long. Sorry about that. But I hope the course generally has been interesting, and I hope this final lecture has been something a little bit different, and maybe just given you a little bit of food for thought. And so don't worry if you didn't follow all of the details. I wouldn't expect that you would. It's more just that there are different ways of thinking about computation. There are different programming languages. They're not all the same. Yeah, so it's a standard thing for people to say, oh, it doesn't matter which programming language I use, they're all the same. Well, if you're talking about R and Python, then they are pretty similar. But that doesn't mean that all languages are basically the same, because a lot of them are not. And so, so I hope it's just, stimulated your thinking about programming, generally programming languages, and maybe even piqued your interest to find out a bit more about functional programming. But anyway, yeah, thanks for making it this far, and hope you've enjoyed the course. Thank you.